Yeah, I think it should work now.
Yeah. Why?
Is it sharing? No, not yet.
Not yet.
Huh?
No,
Not yet. No.
not yet.
Uh,
Yeah, it's
yeah, now
coming
it
now.
should.
Coming.
Yeah.
Okay.
It's coming.
Yes.
Okay, so let me introduce our next speaker. Dr. Rajesh Mahadevan is a faculty member at the Department of Mathematics at the Universidad de Concepcion, Chile. His research works include homogenization and control problems. For now, he will talk about the homogenization of an elliptic equation in a domain with oscillating boundary with non-homogeneous, nonlinear boundary conditions.
Thank you. Thank you. And thanks to the organizers for the invitations and for this opportunity to participate and talk, and to also to get to know many of you. So this is a joint work. This is the topic of this talk is a joint work with Ravi Prakash and Nandakumaran. So like, can you all hear me well? Is it fine? My
Yes, very
yeah,
clear.
okay. Okay, thanks. So I hope, yes. So the problem setting is the following. So you have an oscillating domain with a rapidly oscillating boundary, as is shown in this figure. Here you have a two-dimensional example. So typically the domain has a region which doesn't show much oscillation, which is omega minus, which is below, and then there are like teeth, like structures on the top part of it, of fixed height or of a not so small height, I mean, of a height which is like scale 1, let's say. Um, and so these are like brush or teeth-like structures, like that we saw in the talk by or in the series of lectures by Francois Murat. So this is the domain, and so for example, in Francois Murat's talk, there was no assumption on the periodicity, but here in this talk we take a periodicity assumption on this, and it need not be like histogram like structure, can be also quite varied, as I will show during the later part of the talk. But we assume periodicity in this problem. And what is probably important in this is that, as in Francois Murat's lectures, that um, the teeth-like structures fill up a positive ratio in the upper part of the domain. So when the period is epsilon, so this is the whole scale is L, if you can see my pointer move. So, and between teeth it's of the order epsilon. So as epsilon goes to 0, there are more and more teeth, and in the end they fill up with a ratio theta in the upper portion of the structure. So when you have more and more teeth in the limit, you expect this domain here, whose lateral boundaries are slightly different from the lateral boundaries of this structure, because here it follows this contour, but here it's up straight in the limit. So what is the problem? So you can study several problems in such domains. The problem we consider is the Laplacian, I'm sorry, I pressed on something and it's moving by itself. No. Yeah, sorry. So the Laplacian equation with a lower order term to guarantee the ellipticity in some sense. I mean, and you have a nonlinear condition on a nonlinear Robin condition on the oscillating boundary. On the lower boundary in this, we just assume a Dirichlet condition, but on this oscillating part, you have a nonlinear Robin condition. You could also take here right hand side a non-homogeneous condition which is adequately defined, but for the time being we do not impose such a condition here, so it's not so important. What's probably more interesting in this talk is the Robin condition. And the nonlinearity mu is a typical monotone function in the y variable here, and we assume it to be differentiable in this variable and strongly monotone in the following sense. So under such conditions, the existence of a unique solution to the above problem can be shown in the setup of monotone operators. For example, you can look at corollary 2.2 or proposition 2.3 of the book of Showalter on monotone operators methods in Hilbert spaces. Here, if you look at it, so we assume kind of not more than a linear growth in mu because of these conditions here. And so, but it might be interesting to study other nonlinearities with some LP kind of nonlinearities, might be. So the weak formulation of the above problem is the following. So you have the integral over omega epsilon grad y epsilon grad phi plus integral omega epsilon e epsilon phi plus epsilon. This comes from the Robin condition, epsilon eta over the oscillating boundary gamma epsilon of the term mu x2 y epsilon, and this is the source term. So what are we interested? So we are not really interested in the existence of solution, but rather in what happens as epsilon goes to 0 of the solutions, the asymptotic behavior, and we expect to obtain a limit problem in this limiting domain omega. And what is the main result? So the main result is that in such a case, the oscillating nature of the domain of the boundary here will eliminate some of the derivatives as was seen in the lectures of François Murat. So in the upper part, you will have so the limit y epsilon will have two components, one in the upper part and the other in the lower part. So since it's not defined outside omega epsilon, so we extend it by 0 and we note it by omega e epsilon tilde, and this should converge to a function theta y plus, and in the lower part y epsilon minus will weakly converge in H1, and this convergence in the top is weaker because there is no control over the x1 derivative, so it's only derivable with respect to x2, and the convergence is in a different space, L2 of 0 L H1 M prime, M being the lower level and M prime being the upper level for this this oscillating part of the domain. And so in the upper part you have this equation, which is a kind of homogenized equation. So you have in the limit you have instead of the Laplacian of y, you have only the second partial derivative with respect to x2, and this is multiplied by the filling factor theta, and here also you see that presence. And the Robin condition, which is on the oscillating boundary, will now reappear in as a source term, as a interior term, sorry, and you have it appearing here, and this happens when eta equals 1. So delta eta 1 means it's 1 when eta equals 1 and 0 when eta is different from 1. It's the Kronecker delta function. And on the top part of the new region, you have a homogeneous Neumann condition, and on the interface, which separates the lower and upper part, you have this transmission condition. And in the lower part, it's simply the usual Dirichlet Laplacian equation. So the end result is quite simple, and here you have an explicit characterization of the term which comes as a contribution from the Robin condition, and it's just the mu. It's the same nonlinear function of y plus, which is mu here. Some of these could be quite intuitive, but the appearance of this term is what probably I would like to focus on, because some other parts of this was already discussed in the lectures of François Murat. So how do you prove such a result? So to prove it, you need to begin by getting some a priori estimates, and then to identify a suitable space where you can have some kind of convergence. So it's important for this to have the following kind of Poincaré estimates on the boundary, oscillating boundary, which can be managed. And once you have it, if you go to the weak formulation and take phi equals y epsilon, and since this is a positive term because of the monotonicity assumption, can be dropped, and you will have quite easily the following estimate for the H1 norms of y epsilon. But the problem here is that omega epsilon is an oscillating domain, and since you do not have a zero Dirichlet condition on the oscillating boundary, a simple extension by 0 is not enough to bring it to a fixed domain and do the convergence. So that's the main issue in such problems. So there are probably different approaches. Probably one could look for suitable extension operators and then pass to the limit. But in any case, what is clear is that this uniform estimates for H1 omega epsilon implies in the lower part a uniform estimate for the same sequence, but in restricted to the lower part. And so you have weak convergence in the lower part of y epsilon minus. And this is enough to pass to the limit in the lower part, because actually there's no problem and there's no oscillation or problem any kind in the lower region. but it becomes quite difficult in the upper part. In any case, y epsilon is again bounded in L2. If you extend it by 0, that's no problem. And so the extension by 0 will have a weak limit, and which we can always write it as theta times y plus, since theta is a strictly positive function, the positive filling ratio. And this was done, you can do exactly like in the lectures of Francois Murat, which are available in this lecture series. The diapositives of this lectures are also available, so one can consult his lectures for some of these details. So what's up short? So, but as you will see here, you have gradient terms in this, and to pass to the limit, you still need to manage to say something about the convergence of the gradients of y epsilon in the upper part, which we haven't said anything so far. But if you use suitable test functions like the ones which were shown in Murat's talk, so basically you, for each teeth, you take a test function here, which is in this part, you subtract out from x1 a fixed point in this arbitrarily chosen point in each of these teeth. So if you do that, so obviously the difference is of order epsilon, because this is of order epsilon, this thickness, and you want this function to live in the upper part, so you multiply by a cutoff function, smooth function with compact support in the upper part. And so this is more or less the function which you construct. And if you use these test functions in the weak formulation, which is here, and pass to the limit, then all the terms will drop out except the ones which involve the gradient. And from that, you can conclude that the extension by 0 of the gradient of y epsilon plus has the following structure. So again, the details of this can be seen in the following transparency during the lectures of Francois Murat. So here, so I refer to the section 4.1, 4.2 for more details of how to obtain this structure for the limit of the gradients in the upper part. So without so I'll try to continue from there. So so what do we have so far? We have the weak convergence of y epsilon in the lower part in H1, and then in the upper part you have the L2 weak convergence of the extensions by 0 of y epsilon plus and its gradient, and you can identify them properly. And so you can pass to the limit in all the terms except the terms which involve the gradient, the oscillating boundary, and that's where the difficulty lies. So if you do this, you get exactly like, so you can forget this mu term and you will get all the other terms except this term. So how do we account for this term in the limit problem? So that's the main issue. So this is a problem because you have here a sequence of functions which are nonlinear. I mean, a nonlinearity which is applied to a sequence of functions y epsilon, and they themselves do not converge in any fixed space. On top of that, you have these functions which are evaluated on oscillating domains, meaning which are the surface integrals in the upper part of the domain. So how do you handle convergence in these things? So some of this kind of problems has been studied previously in Gaudiello, paper by Gaudiello and Ricerche Mathematica, and also in Charonescu Donato, and for non-homogeneous Neumann conditions. And also it has been studied for a nonlinear Robin condition in Melnick. So what we will say shortly is not completely new, but the approach we take is different. Because in the previous works, they convert this surface term into a volume term using auxiliary functions, some boundary value problems which are introduced. I can show briefly. So you have here, I don't know if you can see very well this. Let me do full screen.
Yes, we can see properly.
Yeah. Now it's taking its time now. I'm sorry for sloppiness in the presentation. What happened? Here, sorry. So I don't know why I tried to make it full screen. It's like getting stuck now. Sorry, give me a few seconds, please. Yeah. Maybe I can do something different. Yeah. So here is a typical boundary integral. This is an oscillating boundary, and the way they convert to a domain integral on the oscillating domain is using these functions y, which are solutions to some auxiliary problem in which are defined in the following way. And G here is the ratio of the perimeter to the volume of the sections here at every height. So it's a bit technical, but this is the way it was done previously. And the idea of this goes back to some papers by Vaninathan. In this on the other hand, we use the unfolding operator to convert the surface integral into a domain integral and then allow us to pass to the limit. So it's, I think, much more straightforward. And such an idea also has been used previously in Damlamian and Peterson. So the references are at the end of this slides, so you can have also a look at the references. Excuse me, Edita, I mean, how much time do I have left?
20 minutes.
Okay, thank you.
Including the questions.
Yeah, okay, no problem. Yeah.
Okay.
Yeah. So, and there are also maybe other alternatives to handle these kind of surface oscillations using adaptations of the two-scale convergence method by Marianus, Radu, and I won't go into these other ideas, but let me briefly recall the unfolding operator. So the unfolding operator given in, so omega plus epsilon, remember it's the upper part of the domain, which is oscillating. And so you define an operator which takes functions from here and kind of unfolds them into a different space. I mean, you have a function on a different space at the cost of increasing the dimension of the space where you define the function, which means like you basically probably would like to have as many copies of the function as there are like foldings in the domain. So in some sense, that's the idea. So given a function on the oscillating domain, you can construct a new function on a domain without oscillation. So in the upper part, you can like extend the function by 0, and so in between, if you need to like consider values, you take the values as 0, but you also add an extra variable to this function. So the variable basically, if you are at some point x1 in the domain, in this domain, so you could quotient it modulo this period, and so you have like a blown up domain, and zeta 1 is basically all that values you can take in the blown up domain. So you create as many copies as there are like points in the cell, and at each x1 you quotient it out and bring it to the integer part of this in some sense. So if you do that, then there are several properties which can be obtained. So one is this operator is linear, which means that if you have a sum of two functions, it converts to sum, and then if you multiply by a constant, also it gets multiplied by a constant. It also converts products into products, and the other important properties are the integral of the lifted function, let's call t epsilon y, or the unfolded function on this extended or on this like unfolded domain is the same as the integral of the original function multiplied by a factor L, L being the length of the volume in it, as the case may be, of the cell. And if you have a function on the boundary, something similar happens. So, but here you have to take care. So if there are flat parts of the boundary, like it's the case in our example which I showed you, then there it goes through exactly in the same way. So the integral on the flat parts are the same as of the unfolded function is the same as the integral of the function on the flat part multiplied by L. But if you have like oblique or vertical parts, then the integral here of the unfolded function has the following relation with the integral on the vertical parts of the original function. So how do you explain that? So so in some sense, sorry. So if you look at the surface integral, and so you can divide the surface integral into different portions, and on each portion at the same height you have 2 points which are one on this side and one on this side, and these are like point integrals, and so you have a contribution which are like points to the surface integral from these two faces. And so but how many and when you rescale the domain, the point integral doesn't really scale. So but this the original the integral over this domain scales as epsilon, so that will account for more or less in some sense oscillations on a what I mean is that the cells are like d-1 dimensional, and the heights of the oscillations are of amplitude 1. So the same would happen in such cases also. So the scaling is the same even for like 3, 2, 1 or d-1 1 kind of domain. So in the sense of Melnick. So once you have this, and other than that, okay, so some of these are consequences again of some of the points before, which I would not like to go into, but what I would like to mention here is that if now y is a h1 omega epsilon function on the upper domain, so there are these relations, and other than these relations, so the L2 norm of the, I mean this function t epsilon y, the unfolded function, because of the definition, you cannot expect like differentiability with respect to x1. So it's only in L2 of 0 LH1. So it doesn't lose the differentiability in x2, but it loses differentiability in x1, and the unfolded function in any case has this norm estimate. So this is again an important information which you need to keep in mind. So once you have all this information, then one could like to look at this term here and try to see what happens to this. So the first thing to do is to rewrite this using the unfolding and write it on a non-oscillating domain using the unfolding. So you take this function now, which is on the oscillating part of the domain, and then you do the unfolding of this function mu of x2 by epsilon, and by what we saw, you have you can show that this is probably the space is probably a bit confusing here. Maybe it's true. Just a second. Yeah, sure. So the mu composed with y epsilon is in h1 of omega epsilon because of the Lipschitz properties of mu, and so the composition will be in this space. As I said, it will lose some regularity in the x1 variable, and but you have these bounds. So you have weak convergence of the unfolded function in the upper part, and it's also possible to show this the weak limits theta is independent of the x1 variable, which is not evident, but it's possible to show. And once you show that, the integral on the vertical parts, which is what interests us, if you multiply it by epsilon, due to the relation, the unfolding relation here, which you have 1 over epsilon factor. So if you take it to the other side, and here you have to remember to use mu of x2 composed with y plus epsilon. So in that case, you can rewrite in this form. And as I said, you have weak convergence of in this space, and since you have like a h1 dependence in the x2 uh, in also in z1 variable, so you can have a continuous trace, and so the traces converges for this convergence and converge to the same function, because it's this function doesn't depend really on theta 1. So you obtain the limit for this surface term. So and but there is still an issue, like you need to identify this limit theta, and actually you can show that zeta is just mu composed with the limit y plus in the upper part of the domain, and this can be done as is usual for monotone operators using the Minty-Browder technique. So so the details of this are in our paper, so you can have a look at that. So this is more or less what I wanted to say, but before closing, I would like to make a few more remarks. So as I said, the example I showed you, we had were like tooth, but you can also have a periodic function on the upper part, and not necessarily cylindrical, like in like what we saw in paper in the talks by Murab, but these also have been studied in papers by Melnik, so it's not new. And you can do it on other like structures, like a 3D structure where the lower part is a solid thing, and here you have the oscillations, which are like teeth, and the periods are two-dimensional and the height is fixed. So in such domains also you could work, and the results, so if you study a problem on this, and as I said, you could also study a non-homogeneous condition on the oscillating boundary, which is suitably defined. So the limit in such problems can be obtained, and this would be the kind of result you would probably obtain. And here the difference when you have don't have cylinders of a fixed height, but if you have like oscillations which depends, being the volume or the section here, I mean, if you have cylinders of a fixed height, then the filling ratio is the same at any height. But if you have something like this, the filling ratio at any given height is different. So the surface, or I mean the proportion of the area at a given height is height dependent, and so you have instead of a constant factor, you will have a degenerate equation with the coefficient, which is like the area fraction at a given height. So that's what comes into place. And for this, you again use the unfolding technique. So unfolding for such domains also can be easily defined, no problem. And so the above results can be obtained. So, and for more details, you could see the paper and also all the references which are contained there. So this is more or less what I want to say, and thank you for your kind attention. And here are some references.
Okay. Thank you so much, Dr. Rajesh. I think there are some comments and clarifications here. So the first one is a question from Apratim. Does it matter if we extend by some number other than 0? But subsequently answered by Ravi. Of course. By
Just a
Ravi.
minute. I can't see the.
Can you see the chat box?
Sì,
Let me. I think here.
per me, sì, per me qualsiasi orario.
How do I expand it? No.
Maybe you can unshare your screen if you want.
Yes.
So you can.
Oh, God. Yes.
Okay.
Yeah, now, yes. Yeah, so what's the question, please?
Does it matter if we extend by some number other than 0?
I think the extension by 0 is the most like easy, and but the main problem is when you extend by 0, this function doesn't stay in the H1 space. So you need to extend the function also its gradient by 0. And when you take the limits, you need also to see what's the relation between the limits. So meaning what is the real relation between the limit of the extension of the function and the extensions of the gradient. So that was addressed in Mura's lecture. So
there is a long comment here by Prof. Melnick. Can you see that?
let me try to see the chat. Yes.
It's quite long.
Melnick, you said?
Yes.
How do I see all the chats? I can see a few here, but I don't see.
Okay.
Here it is. Is that?
Yes. Okay. It's quite long.
Is this the one? Okay. Yeah. Yeah, meaning probably it's not so general as the works by Professor Taras Melnick. So maybe I was not being very faithful when I said, but the technique is different. So I mean, I just probably you can get stronger results using his techniques, but here with maybe a much simpler technique, but at least the initial results are much probably faster and more straightforward. I would like maybe if Taras would like to continue his comments or write to me, I'm quite welcome to.
If I will understand, the result, the ritual one was I proved 30 years ago. Then Taras proved with H monotone for the Laplacian. I and Taras proved worked with monotone operator in second order terms. If I understand, the novelty of the paper is that you apply the unfolding operator, you can obtain more general structure, if I well understand.
I mean, I don't know. There is only a technical difference in. I don't know if you can. I think the domains which Taras can also study can be quite complicated. So I don't think there's a difference. Meaning, but the results coincide in some sense. But maybe there are like convergence results which you don't prove, and which he probably gets, which we do not.
The other things, the picture you showed with the oscillating
Yes.
boundary, it seems that the density can go to 0 in some points. I think in the reality, you cannot degenerate, no? The density theta. You cannot have a point. I think you are not able to consider domain with some points. I think. I don't know.
I didn't get it. In the picture I showed, yes.
Sure. The bumps are points. Okay, this means that theta is 0 on the top. But I think it's just on the picture. In the reality, you don't consider theta equals 0. That the problem can degenerate.
No, I mean I can consider. So what I don't consider is when at any height.
I think a theta is greater than a constant.
At any height, you need a positive fraction. So
yes, it cannot be 0.
No, it cannot be 0. No.
It's just a problem on picture. Okay.
Yeah.
Thanks.
Yeah.
Okay, so I think there is one more question. So thanks for the nice. Can you handle additional non-linearities in omega epsilon, especially the upper part? In both the oscillating domain and the boundary?
Just excuse me, Taras wants to speak. Can you unmute him?
Okay.
Sure.
ICTS, can you unmute the
Professor
Taras?
Taras Melnik.
Yeah, yes, sir.
Taras Melnik.
Taras. So what's the name?
Taras Melnik. Taras. And Ravi Prakash.
Ravi Prakash. Okay. Yeah. Yes, madam.
So are they unmuted?
Yeah.
Okay.
Yeah.
Yes.
Yeah, so as pointed out by Antonio, that the novelty of the paper was mainly the use of the unfolding operator. That's absolutely fine. And the results, what Taras is saying, he got the very good results in that paper, as mentioned by Antonio as well. And the question of Antonio, that if they are meeting at one point at the top, you cannot convert you will have to leave the limit PD limit equation in the integral form. You cannot go to the PDE because you will not be able to recover the boundary condition at the top part. Okay, so you will start with the PD, and if there is a meeting point, that the notch is going to touching like a ball pen, then the limit PD in the limit you will not get a PD, you will get just integral equation because you cannot recover the boundary condition. Maybe I will talk something like I will try to point out this in my talk.
Yeah, just one.
Okay.
I would like maybe Antonio or Taras can send the papers after 2018, because this work is, although it's 2020 in paper, but it was like 2018 when it got accepted. So
6
Yeah.
15. The work was done in the 14, 15, 14,
Yeah.
15.
Just excuse me, could you open the Taras before Taras wanted to speak? Can you unmute him?
Yes, Taras is unmuted already.
Yes, I am here. I listen you.
Yeah.
You want to speak, Taras?
I have written remarks and I obtain answers of, and I hope Ravi give us additional explanations in his talk tomorrow.
Yeah.
Yeah.
Okay, so more tomorrow. Okay, so thank you very much, Dr. Rajesh, for your talk and for your time. So I think we will get back after 3 hours, right? After 3
Thank you.
hours.
Okay.
Okay.
Yeah, so
Okay. Thank you to
Thank you.
all the speakers, to everybody.
Thank you,
next
everybody.
session
It
is
was a
at
nice talk.
Thank you
next
for the
session is
chair
at
also.
8:30 Indian time after 3 hours.
After 3
Sorry?
hours. After that will be 11 p.m.
11 p.m. for you, India
Yes.
8:30, 4 o'clock for France,
Oh,
Italy, France, Germany, and all that.
yeah, that is.
Okay. So please come back
Yes.
after
Okay,
lunch,
okay, we will
after
come back.
dinner.
Rajesh, I send you a message directly.
Okay. Thank you.
Okay, bye.
Bye.
Okay, see you. Especially thank you for the good discussion. Yeah, this
Yeah.
is what I say, Rajesh. As soon as you do the work, you should publish. It took 2-3.
Okay,
Yeah.
thanks. Bye.
Yeah,
Rajesh did not show the work what delayed the publication.
that is okay, but it is done almost 2016 or something.
No. He added a huge part later, and that he did not show today.
Yeah, okay, fine.
Yeah, I try to keep it as less technical as possible, and
Yeah.
and maybe my explanations I could have improved, but
Yeah, I think you moved from one slide to another slide in a half an hour, 40 minutes talk. That disturbs it. You move
yeah,
so
probably.
Okay, bye. See you.
Bye,
that
see you.
hinder the presentation in a short time.
No, also some
Maybe you
technicals.
discuss directly among us